Look up at the moon tonight, and you're looking at something astronomers have basically taken for granted since before telescopes even existed. But here's a strange fact that might surprise you. We've confirmed more than 6,000 planets orbiting other stars. And in all that searching, across 3 decades of exoplanet hunting, we have never confidently found a single moon orbiting any of them. Not one. How is that possible? Let's start at the beginning. In 1610, Galileo Galilei pointed a brand new telescope at Jupiter and saw 4 small points of light lined up next to it. Night after night, those points moved. They were orbiting Jupiter. He had just discovered the first moons ever confirmed beyond our own, Io, Europa, Ganymede, and Callisto, still called the Galilean moons today. Since then, our catalog of moons has grown enormous. Our own solar system now has more than 300 confirmed moons, from tiny asteroid-sized rocks to Ganymede, which is actually bigger than the planet Mercury. Moons, it turns out, are everywhere close to home. Then in 1995, everything changed again. Astronomers confirmed the first planet ever found orbiting a star like our Sun, 51 Pegasi b. That discovery opened a floodgate. Telescopes got better. Detection methods multiplied. Today we sit at more than 6,000 confirmed exoplanets, with thousands more candidates waiting to be verified. So here's the question worth sitting with for a second. If we can find planets thousands of light years away, tiny worlds we can't even see directly in most cases, why can't we find their moons? The honest answer is that moons are brutally hard to detect. A moon is smaller than its planet, so it blocks less light and tugs less gravity. Most of our best planet hunting techniques are tuned to catch big signals, a planet crossing in front of its star, a star wobbling under a planet's pull. A moon's contribution to that signal is often buried in noise, the astronomical equivalent of trying to hear a whisper at a rock concert. That hasn't stopped people from trying or from getting excited too early. In 2018, astronomers announced a possible exomoon candidate around a planet called Kepler 1625b, a Neptune-sized moon around a Jupiter-sized planet. It made huge headlines. But follow-up studies couldn't agree on whether the signal was real or just noise in the data, and years later, it's still disputed. Other attempts, targeting planets and brown dwarfs discovered by direct imaging, like GQ-LUP-b, and the planets of HR 8799, came back with no clear signal at all. Why does any of this even matter, beyond the pure curiosity of it? Because moons might be some of the best real estate for life in the universe. Right here in our own solar system, Europa and Enceladus, 2 icy moons orbiting Jupiter and Saturn, are considered among the most promising places to search for life beyond Earth, not because they're warmed by their star, they're not, but because the gravitational squeezing of their planet heats their interiors enough to maintain liquid water oceans. A moon doesn't need to sit in the classical habitable zone around a star at all. It can make its own heat. So if moons around planets in our own solar system can potentially host life, what about moons around planets, or brown dwarfs, orbiting entirely different stars? That question has been sitting unanswered for years, waiting for a first confirmed detection to even begin exploring it seriously. Before we get to what one team just found, let's talk about the object at the center of this story, because it's stranger than a regular planet or a regular star. It's called a brown dwarf, sometimes nicknamed a failed star. A brown dwarf forms the same way a star does, out of a collapsing cloud of gas, but it never gathers quite enough mass to ignite the nuclear fusion that powers stars like our Sun. Instead of shining for billions of years, it just slowly cools and dims, glowing faintly in infrared light for the rest of its existence. The dividing line is mass. Below roughly 13 times the mass of Jupiter, an object is classified as a planet. Above about 80 times Jupiter's mass, it gathers enough material to become a true hydrogen-fusing star. Everything in between exists in this strange middle ground, too big to be a planet by strict definition, too small to shine like a star. The brown dwarf at the heart of this discovery sits deep in that middle ground. It's called CD 35 2722b, roughly 70 light-years from Earth in the constellation Columba, first spotted through direct imaging back in 2011. It's about 37 times the mass of Jupiter, orbiting a small, young red dwarf star with roughly half the mass of our Sun. And crucially, this whole system is young, part of a stellar family called the AB Doradus Association, only around 100 million years old. For comparison, our own solar system is about 6 billion years old, meaning this system is still practically a newborn on cosmic timescales. Why would astronomers pick this particular, obscure-sounding object out of the thousands of known brown dwarfs and directly imaged companions to study for years? Because it's uniquely well-positioned. It sits far enough from its host star that a telescope can separate its light almost completely, cutting out the kind of stellar contamination that ruins these measurements for closer-in companions. If a moon were going to reveal itself anywhere, calculations suggested this system gave researchers about as good a shot as they were going to get. So a team of astronomers, led by researchers working in Chile, set out to watch this brown dwarf closely for more than a year, hoping to catch the faintest of gravitational fingerprints. Here's exactly what they did. Using the Cryers Plus instrument on the European Southern Observatory's very large telescope in Chile, the team applied a technique called radial velocity analysis, the same method used to confirm that very first exoplanet, 51 Pegasi b, back in 1995. Radial velocity works by measuring incredibly tiny shifts in an object's light as something orbiting it tugs it slightly back and forth. Between October 2023 and January 2025, the team collected 21 separate observations of CD 35 2722b using this method. And a signal emerged. A clear, repeating pattern showed something tugging on the brown dwarf every 169 days. When the researchers modeled that signal, the best explanation wasn't one companion object. It was two. The larger candidate has a minimum mass of about 74 times the mass of Jupiter, on a nearly circular orbit lasting 169 days. A second, smaller and less certain candidate weighs in at a minimum of roughly 28 Jupiter masses, on a shorter orbit of about 87 days. Their orbital periods sit very close to what's called a 2-to-1 resonance, meaning the inner one completes almost exactly 2 orbits for every 1 orbit of the outer one. That's not a coincidence pattern invented for this system. It's the same rhythm locking together Io and Europa, 2 of Jupiter's own Galilean moons, right here in our solar system. Compare the scale of these objects to anything we know locally. The larger candidate satellite weighs in at about 2% of its brown dwarf's mass. The smaller one comes in at roughly 7%. For context, the largest mass ratio between any planet and moon in our entire solar system belongs to the Earth-Moon system at 2%. Both of these newly detected candidates would outrank that record. These would be, relative to what they orbit, unusually massive moons, more consistent with how giant planets themselves are thought to form far from their star, rather than how smaller rocky moons like our own typically form. Before calling this a real detection, the team had to rule out every boring explanation that could fake a signal like this. Could it be some artifact of Earth's own yearly orbit around the Sun, contaminating the data? They checked and found no such correlation. Could it be drift in the telescope's instruments? Checked, ruled out. Could the brown dwarf's own rotation be creating the wobble? This one mattered a lot because brown dwarfs can have starspot-like features that fake a periodic signal. But CD 35 2722b is expected to complete a full rotation in roughly 16 hours, thousands of times faster than the 169-day signal they detected. There is no way rotation alone could explain a signal that slow. With those alternative explanations eliminated one by one, the researchers describe this as the most compelling evidence yet for a satellite, or satellites, orbiting a brown dwarf beyond our solar system, the strongest signal of its kind ever recorded. But they're careful and honest about where this stands right now. This is a candidate detection, not a fully confirmed discovery. The smaller, second satellite signal in particular still carries real uncertainty about its exact orbital period. Follow-up observations, watching this system for more years, will be needed to nail down the orbits, with the precision needed to call this case fully closed. And there's one more twist. This discovery is already forcing scientists to argue about what a moon even is. Because both the brown dwarf and its candidate satellites are so unusually massive, one of them not much lighter than a large planet itself, this system falls into a genuine gray zone between moon, planet, and star that our current astronomical definitions were simply never built to handle. The researchers behind this work argue that objects like this one may eventually need an entirely new category of their own, rather than being squeezed into vocabulary invented to describe our own, much smaller-scale solar system. So the next time you glance up at our own familiar moon, remember, it may not be alone in the universe after all. Somewhere around a young, dim, failed star 70 light-years away, something that might be the first confirmed moon beyond our solar system could be quietly completing its 169-day orbit right now, waiting for one more observation to make it official. This video was based directly on the peer-reviewed study, Planetary-Mass Exosatellite detected around the substellar companion of a star, by Kevin Hoy and colleagues, accepted for publication in the journal Nature in 2026, with its findings openly available for anyone who wants to review the data themselves.